well, basically to fit a function, fx equals y. That's supervised learning, and we covered a little bit about unsupervised learning as well. In particular, we learned K-means clustering, and a more sophisticated technique called Gaussian mixture model, right? And those methods are usually used for clustering, right, which is a very typical unsupervised learning method. So today we are going to talk a technique which is in between, right? It's called semi-supervised learning. So as the name indicates, I guess it's pretty straightforward. Which means the setting is now you have a bunch of labeled data plus a bunch of unlabeled data, maybe more unlabeled data, because it's very easy to get unlabeled data, right? Okay, so this slide just shows example of supervised learning. For example, to train a classifier to distinguish junk mails from, important messages, right? I guess we don't have to go through this, right? So basically, you can either train a support vector machine or Decision tree or random forest or boosted tree, things like that. And once you train the model, you can use that to predict on unseen testing data. And in terms of the performance, usually the supervised learning will give you the best performance under the conditions that you have sufficient labeled data. But in many cases, to label a lot of data is time consuming, and it can be very costly, right? And actually, for some application, it's not even possible to label a lot of data. In contrast, the unlabeled data is much cheaper, right? For example, if you want to develop an image classifier using unlabeled data based on some unsupervised learning, then you can pretty much say just write some code to harvest the images from internet using, say, Google image engine, search engine on Bing image search engine, right? But those images will not give you, will not have a good label, right? It can be very noisy. So you have to come up with some technique to use those data. So here, I just give you some examples of unlabeled data. This is speech analysis. All right, so this here we have this, research question, right? Can we make use of those cheap unlabeled data, right? And how can we design effective methods to take advantage of those cheap unlabeled data? So in the setting of, as I said, in the setting of semi-supervised learning, we do have access to a small number of labeled data, right? But then, we may have a much bigger, unlabeled data set. So now, then the research problem is we need to design some algorithm. Here we call it semi-supervised learning methods, right? Which can take advantage of those unlabeled data. And after the learning, after the training, the accuracy should be better than you using those labeled data alone, right? Otherwise, it's useless, right? It doesn't make any sense, right? Of course, the performance should be better than using labeled data alone. So, which means we need some algorithm which can, improve the accuracy or the generalization capability compared with, purely supervised learning. Okay, so this semi-supervised learning, it's in machine learning, it's still a very active research topic, right? So a lot of algorithms already been designed, but so far, pretty much it's still an open problem. Well, same as unsupervised learning, there's no much breakthrough in the past few years. Actually, so far, no semi-supervised learning methods can guarantee that if you use unlabeled data, the performance must be improved compared with using labeled data alone. Right? There's no such a guarantee. That's a problem of most semi-supervised learning methods. Okay, so we're going to study a few unsupervised learning methods today. Right, so the first method is called co-training. Actually, it's a little bit heuristic, and it's not a particular method. It's actually a family of methods. Right? It's like a meta algorithm. So it's proposed like 20 years ago. So the observation is that many problems can have two different sources, actually multiple different sources of information you can use to predict the label. Here we just assume that we have two different sources of information. Actually, after this paper was published, there's another work called tri-training or something like that, right? You can imagine in terms of tri-training, which, the setting is that you have three different sources of information. Okay, let's assume we have two different sources of information. Here, let's just check this example. If we want to classify web pages, right? So in a typical web page, we have the text information, the contact information. At the same time, we have this, this hyperlinks, this web links information as well, right? So then the idea is, if we want to classify such web pages, can we use the text, the words on this web page, as well as the words on links pointing to the pages, right? We want to use these two very different informations. Okay, so the basic idea of co-training is to use a small set of labeled sample to learn some initial model, initial prediction rules. For example, colleagues pointing to a page is a good indicator that it might be a faculty homepage, right? And say if the algorithm sees some words like I'm teaching machine learning courses on a page, then it's a good indicator that it's a faculty homepage, right? So then we can look for unlabeled examples. On those examples, one rule is confident, and the other one might not be that confident, right? So then we can use that model, that rule, to label the examples for the other. It's like bootstrapping, right? We have two models. One is confident, one is less confident. We can use the confident one to help labeling, data. So then in this case, we can train two classifiers, one on each type of information, right? Each type of complementary information, right? If the two sources of information are highly correlated, then maybe it's useless, right? This idea will not work because essentially you are using the same information. So these two sources of information ideally should be complementary and say orthogonal to each other, right? And then we can use this very simple idea, to use each to help train the other. In computer vision, actually, after the original co-training paper was applied to text analysis. Later, this idea was applied to some computer vision problems. Here, just give you some examples. Right? So this 2003 paper, they apply this idea for object detection, actually, in this case, to detect the vehicles. And this is named entity extraction. It's a problem in natural language processing, and turns out that you can use this idea for this problem as well. Here, just here some examples of the co-training on the simple problem of web page classification. So in this case, we have 12 labeled examples and a much bigger, data set of unlabeled examples, right? And you can see that co-training indeed improves the performance. So this is the co-training iterations. Right? And the y-axis is the error. So you can see the error actually, the trend is it's going down.
How many labeled examples does that sort of degrade after? Like if you give the supervised algorithm 50, is now co-training no longer advantageous, or they didn't really talk about that in the paper?
I believe the paper does have some empirical results. Okay. But actually, as I said, this algorithm is actually heuristic, which means sometimes it works, sometimes it doesn't. As you can imagine, only if one of the classifier is very confident, which means it works very well, then it's most likely it will work well. Just imagine if you use a small set of labeled data to train, say, two classifiers, and both are not very accurate, both are very weak, and you use one of the very weak classifier to help label the data, the label will be very noisy. And in that case, you add the noisy labels to train the second one, it will fail, right? So again, it's heuristic, so it's hard to know. Let's put it this way: it's task dependent, right? All right. So another example is this computer vision problem. And well, again, initially they only use 50 labeled images and 22,000 unlabeled images. So in this case, it actually worked. The improvement is significant. Okay, so this is yes.
So you're still ultimately relying on your small set of labeled data.
Yes.
To just sort of train two.
Well, train the first one, let's say.
But are you going to train two mutually exclusive classifiers, or?
No. You can just use a small set of labeled data to train, say, the first classifier, right? And use under the assumption that the first classifier, which was trained using the small labeled data, is good enough, then you can use that one to label those unlabeled data, right? And then help each other.
So you're still only training one classifier
to start with. To start with, you only need to train one classifier.
And then you just use that single
to label, well, you do it iteratively, actually. You don't.
The way that I understood it was that you train one classifier on one type of label learning and the other on another. So like for the web pages, you train one on the links data and one on the contents data. Yeah. And then you use whichever one is more confident to like fill the gaps and teach the other one.
So you then have to set
well, I guess I guess you're right. I mean, it depends on the problem, right? So I believe for the text, for the web page classification, you don't need. Let's put it this way. You don't need for the links. It's kind of the label is very easy to get, right? You don't have to manually label all the web pages.
So you have a small set of, I guess, supervised samples for
Labeled sample for both tasks.
links, you train two, and then the remaining you just pick the best.
Yeah. Yeah. All right. So as I said, this is like a meta-learning algorithm. The classifier you train can be any classifier, right? It's really a task-dependent, data-dependent. All right. So the second category of algorithm we want to cover in this case is for semi-supervised learning is semi-supervised support vector machines. So we have already studied support vector machines, but for the case of supervised learning, right, which means you only use labeled data. So this method in the literature, it's also called transductive support vector machine. It's more principled than this co-training idea. All right, so let's just recall the idea of support vector machine. So here, let's check the first plot. It's support vector machine, right? So given, in the case of binary classification, given two sets of labels, negative data and positive data, we try to find a hyperplane which maximize the margin, right? That's standard supervised support vector machine. Okay, so now in this semi-supervised learning setting, we try to use those unlabeled data as well, right? Not just the labeled data. So now the idea becomes, we try to find a classifier, separator with large margin with respect to the labeled data and unlabeled data, right? Here, let's use the symbol L to denote labeled data and the U to denote unlabeled data. So, right, just check this plot. Those circles represent unlabeled data, right? So apparently, if we still use the first, the hyperplane, which was found using the standard support vector machine, then you can see some of the some of the data will be on the, wrong side, right? In this case, really the hyperplane should be this one, right? Such that this margin will be maximized. Okay, so then how do we formulate the optimization problem and find this hyperplane with both labeled data and unlabeled data? When we already know that for the standard support vector machine, the formulated optimization problem is convex. Actually, it's quadratic, right? And you can always find a globally optimal solution. Right? Of course, the optimization problem is polynomial time. In the case of unlabeled data, because semi-supervised support vector machine, because of those unlabeled data, the formulated problem is NP-hard. Right? It's highly non-convex, actually, which means you will not be able to find a global optimum. There are a few ideas. So the simplest one is you can always, it's kind of similar to the co-training, right? So you start with training standard spot vector machine using the labeled data alone, right? And then, after you train this spot vector machine, you can label the unlabeled data. And then try, flipping labels in a greedy fashion. Right? You do it iteratively. Yes?
Is this similar to like Gaussian clustering? Wouldn't this sort of mean
Similar to Gaussian clustering.
Yeah.
Yeah, I mean, the connection is that both actually consider the density. Right? In the clustering, it's basically just the,
So you're effectively splitting it into
two sets.
two sets.
Yeah.
But you're saying there's not much crossover in terms
The idea is different, right? And the formulated mathematical problem is very different, right?
I imagine the clustering method isn't NP-hard though, is it?
Clustering method, in Gaussian mixture model, it is NP-hard. It is NP-hard in the sense that you can only find the local optimum in Gaussian mixed model. Right? You are not able to find a globally optimal solution. So
It's still computationally as expensive.
I guess it's at the same level of difficulty, right? Both are NP-hard. Both involves like two sets of variables. Here you also have two sets of variables. One is the label, one is the parameters of the support vector machine, right? Okay, so actually, the second optimization method is using branch and bound. Branch and bound is an optimization method for like discrete optimization problems. But it's still NP-hard, of course. It's the problem is still NP-hard, and the computation complexity of branch and bound is exponential. It's not polynomial, right? It's exponential in terms of the number of variables. Here, it's the number of unlabeled data points. Okay. But the good thing about the branch and bound it's not heuristic. It's actually deterministic, and typically it will find a better solution. But again, it's computationally heavy, so you will not be able to apply branch and bound to large scale data set. All right, so let's check the loss function of this semi-simplified spot vector machines. All right, this one is the hinge loss, right? So this one is the loss function of the standard support vector machine. And as you can see, it's convex, okay? So it's an upper bound of the non-convex 0-1 loss. So this is the support vector machine's loss function. And this one is logit, right? This one is the like a smoothed version of hinge loss. Okay, actually this is the this is also a upper bound of the 0-1 loss. Right? It's actually used in boosting and logistic regression, for example. Right? So, but it's still convex, right? And the other two, okay, this one. Let's check this one. This is like a what? Like a hat. Okay, it's called a symmetric hinge loss. Right? And this is not convex, of course, as you can see, the shape of the curve. It's not convex. Okay? It's not convex. It's not concave either. Right? And we can use this kind of loss for semi-superlearning. And this entropy loss is just a smoothed version of this symmetric hinge loss. Okay? So the last, so this one and this one are used for semi-superlearning. Why is that? Can anybody tell me why you can actually use this loss for semi-superlearning? Why is this hinge loss is used for superlearning? Yep.
You can't sort of run away into terrible.
Yeah, it will not incur, extremely large loss, right? It's bounded, right? It's upper bounded actually, but for the hinge loss and the this logit loss or exponential loss, they are not bounded, right? It can go infinitely, right? So that's the well, mathematically, that's the reason, as you said.
We don't check the loss. Well, we can't because there's no labels.
That's right, exactly. That's the underlying, well, physical reason why this loss must be like a symmetrical, why it must be upper bounded, okay? Because we don't have the label, right? We don't have the label. So all we have is, okay, so, we want to maximize the margin, right? We don't access the label, so we don't want the loss can go infinitely. All right, so okay, so if you check this loss function because it's non-convex, that's why the makes the optimization problem very challenging. Okay, so here just give you some examples. So we have a very small set of labeled data. So these circles and these stars, those represent two classes, right? And originally, so the standard support vector machine will give you this margin, this solid line, of course, right? And if you have a much bigger set of this unlabeled data, those squares, unlabeled data, then if you can consider both the labeled data and the unlabeled data, of course, this dashed line will be, a better separate than this solid line, right? All right, so that's the second semi-supervised learning method called transductive semi-supervised support vector machine. I'm not expecting you guys can solve the optimizing problem, but you do need to understand the high-level idea, how it works, right? And what kind of loss function. What the difference is between the loss function of semi-supervised learning and fully supervised learning. Okay, the third category of semi-supervised learning methods is called graph-based methods or Laplacian-based methods. In terms of the optimization, it's much easier, much more elegant than the second category of semi-supervised learning. Okay, so the assumption we make is we believe that very similar example probably would have the same label. Okay, so in the feature space, if we have two examples, x1 and x2, they look very similar, which means the distance between x1 and x2 are very small. Then it's more likely those two labels will have the same label. Those two examples will have the same label. Actually, this is the idea of K-nearest-neighbor, right? So in K-nearest-neighbor classification, we, given a test, we find the example in the training data set, which has the smallest distance, right? And you assign that that example's label to the test data. So this is a reasonable assumption. So if we have a lot of labeled data, and this is like K-nearest-neighbor, right? So, but what if you have a lot of unlabeled data, right? K-nearest-neighbor will not be able to use unlabeled data. So the idea is that probably we can use them as as stepping stones, right? So here, just give you an example. If you, let's say, for this handwritten digits, if we have only two samples, right? These two samples do not look very similar. But what if we in between these two, we have another 4 training examples. And if we look at those training examples as a whole, you now are more confident to predict these 2 digits will have the same label, right? So this, 4 digits in between serve as like a stepping stones, right? Stepping examples. So that's the high-level idea, right? So now we need to mathematically formulate this idea such that we can solve it. We can find the parameters of the models. All right. So mathematically, the first step is to construct a graph with edges between very similar examples. Here, very similar examples means we can say just find the K-nearest-neighbor, right? We can find either 1 nearest neighbor or 5 nearest neighbor. Just find the K-nearest-neighbor, and then connect them, right? Those nearest neighbors will be connected by a edge, okay? So here, just show you an example, right? That's the, for example, this 8 and this 8. They are nearest neighbors, so they are connected. So now this unlabeled data can help glue the objects of the same class together, right? Okay, so this is the first step to construct the graph. All right, so here I just show you another example. Actually, that's the actually this is a very good application, like image classification or object classification in videos, right? Because of this temporal smoothness along the time axis in videos, so we can somehow take advantage of that. All right. So after we construct the graph, we actually calculate the so-called Laplacian matrix, actually, which measures the which encodes the neighborhood or the connection information of the graph, and then we formulate the object function and solve it. So here I just show you some examples. All right, so the typical one is, we call it Laplacian support vector machine. All right. This Laplacian matrix is calculated based on the graph we constructed. Let's check this one. Okay, let's check this object function. If you check the first term, sorry, this is the second term, right? The first term, of course, that's the regularization. This looks very similar. Okay, let's check the second term. Here, L means labeled data set. Okay, so this is the hinge loss, right? This is the hinge loss. Hinge loss on the labeled data. So this is the first two terms represent the standard supervised support vector machine. Okay, and for this Laplacian support vector machine, we have the third term. All right, we have this term, and this term are constructed using the unlabeled data, using the graph we just constructed in the first step. Actually, it's pretty straightforward, and it's easy to understand. This S matrix, this one, okay. This, of course, if you check just one value, this is the similarity score. Okay, so this is a similarity score between two data points. And what is this? This is the classifier's score on data point X and data point X prime, right? All right, so we want to minimize this value as well. And this third term actually encodes the idea of, we want, if two data points look similar, then the classification score on these two data points should be small. Okay, if they look similar, then the scores should be small. If X and X prime are the same, then the score should be same too, right? And if we rewrite the third term in a compact matrix format, then this is just something like this, right? F is the classification score, and here L is a matrix. It's called the Laplacian matrix. It's calculated using the graph. Okay, so semi-supervised learning is is active, as I said, active research area in machine learning. It's largely unsolved, and actually, as I said, we don't even have a semi-supervised learning algorithm which guarantees that if you use the unlabeled data, the performance will be always improved. There's no such a guarantee. So when you apply semi-supervised learning to real-world problem, you need to be very careful, right? Because if you don't, apply it properly, or you choose the wrong algorithm, the performance might even drop. Right? And automatic methods of collecting data makes it more important than ever to develop methods to make sure to make use of unlabeled data. Especially like last 2 weeks, we're talking about deep learning. You know, in the age of deep learning, now we need a large training data set. And in most of the cases, it's very expensive and time-consuming to label a large data set, right? Which makes unsupervised learning and semi-supervised learning become even more important. There are quite a few semi-supervised learning methods in the literature, and in this lecture, we only cover a few. All right, so I expect you guys to understand the high-level idea, but not probably not the detailed mathematics formulation. Only if you are interested in knowing more, you can check, for example, the Laplacian support vector machine. You can always Google and to get the to find the underlying mathematics, right? In practice, actually, the Laplacian support vector machine is more practical than the other two that we talked about today. Mainly because the Laplacian matrix, the Laplacian support vector machine, the optimization problem is still convex, which means you can still find a global optimum for Laplacian support vector machine. And it's kind of straightforward, right? You just compare it with the standard support vector machine, you only have one more term in the objective function, right? It actually serves like another regularization term. All right, so I guess we have some more time. Let's briefly talk about the manifold learning. The original plan is to have one lecture to talk about manifold learning, but maybe we'll have like a half hour or something to talk about manifold learning. And this is the third assignment. All right. So a few weeks ago, we studied PCA and LDA, right? Principal component analysis and linear discriminant analysis. We mainly studied the linear version of both methods, but talked a little bit about the kernel extension of PCA and LDA. Next week, we might spend a little bit more time on kernel PCA, kernel LDA, actually in general, how we kernelize a linear algorithm to make it nonlinear. So those PCA, LDA, KPCA, KLDA, they are typical examples of a more broad category of learning methods called manifold learning. Okay, so in the case of linear subspace learning like PCA, LDA, which means the manifold is linear, right? But more importantly, in real-world data sets, usually the underlying manifold can be nonlinear, right, in most of the cases. So here, I just show you an example. Let's say we have 3D data points, something like this, right? And somehow, if we just unfold it, right? Unfold it into the third plot, right? So now the third dimension disappeared, right? So the original 3D data becomes 2D, right? So which means the underlying dimension of this original data actually it's lower than it appears to be, right? The original dimension is 3D, and it's actually the underlying space is only 2D. So the research problem is how we find the underlying low dimension space, or, in other words, how we unfold the original data, right? We might cover, a few different methods here. Again, for the third assignment, you really should read all the papers, right? So the relevant papers on MDS, ISOMAP, LLE, SDE are all in the third assignment. You should read the PDFs. And actually, these are, the successful manifold learning methods, and they actually share some connections. They are not completely independent. Right? So why dimensionality reduction? We covered this when we learned this PCA LDA, right? For a few reasons. One is, the original data set may be, very high dimensional, right? It can be hundreds of thousands dimension, and it's difficult to process such high dimension data. So we want to project it into a low dimension, right? Such that the computation in the low dimension space becomes much easier. That's one of the important reasons. The other is the original data typically contain noise, right? By projecting the original data into a low dimension space, we actually remove some of the noise, right? It's a procedure of noise removal. And also, if we can somehow project the data into 2D or 3D, or maybe even 1D, then we can visualize the data. For any dimension higher than 3D, it's not possible for us to visualize the data. Okay, so here just give you some example of image data. So let's say we have a set of this kind of facial images, right? The original data is actually, the dimension of the original data is the number of pixels, right? If the image size is 100 pixels by 100 pixels, then this is 10,000 dimension. So it's very high dimension. But then if you check this data set, right? This data set, the variance, the distribution of the facial images, really, it's just the pose, right? The facial pose, because in this data set, it's the same person, right? Just different pose. So which means the underlying dimension can be very small. It's just the angles, right? The orientation angles of the faces. So so by pixels it will be very high dimension, but then perceptually meaningful structure it's just a 3D. It's the pose of the facial images, right? So in this case, pretty much we can project the original data into 3D. Right? Okay. So this is the example I just showed you, right? It's the original data is 3D, but there is the underlying dimension, the intrinsic dimension, can be 2D, right? All right. So in the language of probability, so we have the observed data, but we want to uncover the latent variables, right? So it becomes, if we put it into a Bayesian framework, Bayesian estimation framework, we need to estimate the latent variable. So PCA, okay, so we already studied this, right? PCA finds the direction that, of course, the standard PCA is linear. So the find a linear projection. We project the original data into 1D, and along in this 1D space, the variance of the data becomes maximal, right? It has the largest variance. Then we find another linear projection to project the original data to the second 1D space, which is the second 1D space is orthogonal to the first one. And along the second one, again, we have the largest variance. Right. So check this example. If we given such a data set, this will be the first direction, first axis of PCA, because along this direction, the variance of the data becomes largest. And the second one will be in this direction, right? Orthogonal to the first one, so it will be that direction. All right? I might skip this one. So the calculation mainly involves eigen decomposition or singular variate decomposition, right? EVD or SVD. Okay, so this classic MDS, it's related to PCA. It can be viewed as a generalization or extension to the original PCA. So again, we calculate the pairwise distance matrix. Right? This is pretty much similar to what we do for this the Laplacian SVM. We need to construct a graph, the neighborhood graph. All right. Okay, so in this case, it's fully connected graph. So we calculate all possible pairwise distance. And we want to find a low dimension embedding space, right? Low dimension manifold, right? From X to Y, such that in the low dimension space, this distance almost is the same, right, to the original distance. So in other words, given a bunch of data set, right, and we want to project each data set into a low dimension space. And in that low dimension space, the pairwise distance are preserved, right, are kept the same, well, approximately, of course, right? If we want to strictly make the distance the same, then the problem becomes infeasible, and you will not be able to find such a embedding space. So that's the idea, right? To keep, to preserve the pairwise distance in the embedding space. All right, so this is the object function, right? We of course calculate the original pairwise distance, and we minus the distance, the pairwise distance in the embedded space, in the latent space, and we minimize the error, the difference of the distance, right? Okay, so the optimization becomes try to find this the embedded data points of the original one. Right? I might skip the mathematics here, but pretty much the optimization mainly involves eigen decomposition again. It's as I said, it's a generalization of the PCA. So you calculate the distance matrix, and the output is a coordinate of the latent representation, right? Of the lower dimension space. So this G is a gram distance, gram matrix. It's calculated from the distance matrix. And then you do a eigendecomposition, and then the coordinate will be the eigenvectors, okay, scaled by the eigenvalue. So they share some similarities between the MDS and PCA. All right, so both PCA and MDS, they are linear, right? We find the linear projection, but if you check this example, it's highly nonlinear, right? A linear projection will not give you very good result. So we want to generalize to, nonlinear manifolds. That's the idea of isomap, LLE, and SDE. Okay, so let's check isomap. The idea of isomap is, well, compared with MDS, the only difference is the way to calculate the pairwise distance between data points. When we calculate the Euclidean distance between data points, we actually make an assumption that this manifold is linear, right? If the manifold is nonlinear, then we should not use Euclidean distance to calculate the pairwise distance between points. Here, just give you an example. So, if we have such a data set and given these 2 points, right? If you use MDS, then it's just this. The distance is this. The length of this straight line, right? But this distance does not. This straight line does not represent the true distance between these 2 data points, right? Because there's no these 2 data points should not be connected if we say build a graph, build a Laplacian graph. They are not considered as neighbors, right? Semantically, these 2 data points are far away from each other. So the true distance should be, you really should calculate the length of this curve. It should go this path, okay, instead of this dashed straight line, all right? So that's the high-level idea, right? So in order to, precisely represent the distance of these 2 data points, you really should calculate the length of this curve. And this is called a geodesic distance, okay? So this is not Euclidean distance. Euclidean distance is just calculate the L2 norm, right, of the difference of these 2 points, right? So now instead you should calculate the length of this curve, this nonlinear curve. And we use, well, basically we need to calculate the geodesic distance. And how we do that? So the high-level idea is use geodesic distance rather than Euclidean distance in MDS. So that's the only difference, right? If we calculate the geodesic distance, and the remaining calculation keeps the same, then this is so-called isomap, And the question is how we compute geodesic distance without knowing the manifold. Right? This is like a chicken and egg problem. If we know the manifold, then it's very easy to calculate the geodesic distance. If we know the geodesic distance, we can uncover the manifold using eigen decomposition. All right, so in IceMap, we actually calculate the approximate geodesic distance, right? So again, look at this example. If we already uncover this, unfold this 3D into 2D, then the distance between these two data points, now it's the Euclidean distance in the unfolded manifold, right? This straight line, but we haven't done that, right? We don't know how do you find the manifold actually. That's the problem we want to solve. So instead, we can calculate this approximate distance. So what we do is we can just connect. We construct the neighborhood graph, and we calculate the shortest path through the graph, right? We find the nearest neighbor, and we calculate the again using the the neighbors as a stepping stone, right? Stepping points, and then find this shortest path between these 2 points. Use that as the geodesic distance. So the step 1 is build the neighborhood graph. This is the same as what we mentioned in the Laplacian support vector machine, right? Using k-nearest neighbor, or the second option is using neighbors within a fixed distance. And there's an algorithm to calculate all pairs, shortest path algorithm. The complexity is n squared log n plus n squared times k. So it's not too bad, actually. It's almost just the quadratic in terms of number of data points, right? Slightly worse than quadratic. N is the number of data points, right? So that's the graph we construct. And then the remaining part is the same as the MDS. And we just do eigen decomposition and find the coordinates. That's IceMap. This paper is very, it's a breakthrough work in machine learning. Actually, this paper was published in Science, the journal Science, around 2000. It has tens of thousands of citations now. Okay, so let's some advantage and disadvantage of IceMap. I'll just skip that. Okay, so the second nonlinear manifold learning method is LLE. It's local linear embedding. It's another method, alternative to the IceMap. The LLE tried to preserve the local manifold geometry in its embedding. Okay, so it's different from the IceMap. Right, IceMap is pretty much, MDS preserves the Euclidean pairwise distance in the embedded space, and the MDS. The IceMap preserves the geodesic distance in the embedding, right? But here, the locally linear embedding preserves the local manifold geometry in the embedding. So the high-level idea is, okay, the given bunch of data, the underlying manifold might be nonlinear. Right? If it's linear, then you just apply PCA, things like that. Might be nonlinear, but we assume in a small local neighborhood, the geometry, the manifold, is linear, right? As long as the neighborhood is small enough, we can always make such an assumption. So then in the embedded space, we try to preserve the local linear geometry. So assume the manifold is locally linear, which means we expect each high dimension data point to lie on or near a locally linear patch of the manifold. So just check this point, right? Check this plot, which means, let's say, given a data point, and we choose a small patch. This small patch is locally linear, which means within this small patch, we can safely use Euclidean distance to measure the similarity or dissimilarity of data points. And then we characterize each data point as a convex linear combination of its k-nearest neighbors, right? And then we find the embeddings that preserve those weights, okay? So in this linear, locally linear neighborhood, given a data point, we can always represent this particular data point as a weighted sum of its neighbors, okay? And then we calculate the weight of its neighbors. And in the embedded space, we preserve the weights, which means we preserve the local neighborhood relationship, okay, in the embedded space as well, which means the original space and the embedded space, they share the same local neighborhood information. Okay, so that's the high-level idea, and if we formulate the idea with, mathematically, then we get such a optimization problem. The constraint is subject to sum j, wij equals 1. Okay, this is not minus, okay, this is equal 1. Okay, that's a normalization because it's, as I said, it's a convex linear combination. So W is the weight, right? And this is like given a data point, you find a weighted sum of its neighbors to represent the original data for each data. And we can also solve it using eigen decomposition again. All right, so that's the high-level idea of ALLE. And this method was actually published in the same journal of the ISOMAP. Some examples. If we have such a data set, that's the manifold of the original data. Then if we apply ALLE, you unfold the data into 2D, and you get something like this, right? If we have such a data set like some data points on a sphere, then you get something like this if you unfold it. Here, just show you a comparison between PCA and ALLE. So that's the facial images, right? Which means if you use ALLE, actually it works better because pretty much because the original image data is not linear, right? So if you apply PCA, you can see the distortion compared with the LOE. All right, another example. Just skip some of this. Because you need to first construct the neighborhood graph, right? Let's say if you use k-nearest neighbor to construct a graph, then this parameter of k is important, right? Same as in k-nearest neighbor, right? We mentioned this. You always need to find, a proper k using, let's say, cross-validation. All right, so advantage and disadvantage of LE. I just skip this. A comparison between IceMap and LE. All right, so so the last one, it's called semi-definite embedding. Sometimes it's just also called maximum variance embedding, MVE. Okay, actually later it's renamed as a maximum variance embedding. So just recall, in PCA, right, we actually find the projected space, and in that space, the variance is maximum, right? So in PCA, the objective function can be formulated as maximizing the variance along some direction, linear direction. And here, SDE or MVE, it's just generalize this idea of PCA into nonlinear manifold learning. So yeah, also known as maximum variance unfolding. So we want corresponding neighborhoods of inputs and outputs to be related by translation and rotation. That's not important. So okay, so this plot just gives you a very intuitive idea of how SDE or MVU works, right? Just imagine each input point is a ball connected to its nearest neighbors with steel rods, for example. The steel rods fix the angles and distance between nearest neighbors, and we want to unfold it, right? In this case, if you pull away this graph to two different opposite directions, then we get something like this, right? So this will be the unfolded space. That's the high-level idea. Okay, and if we maximize Euclidean distance between non-neighboring points, the steel rods ensure that we maintain local neighborhood structure, okay, eventually pushing the manifold to unfold. Right? Here are just some. Okay, so mathematically, we want this Euclidean, the local Euclidean distance of some of the connected data points, which means these two data points are neighbors, right? In the embedded space, should be the same as the original distance, right? Again, compare with MDS, it shares similar ideas. Or compare with IceMap as well, right? So the first set of constraints is something like this, right? So if you measure the distance in the original space and the embedded space, they should be the same. And we can center the projected data on origin to to take the mean, right? Because it's translation invariant, so we can always impose such the first constraint just to make the coordinate in the origin. And the object function then becomes the maximize the variance. Okay, so the sum ij yi minus yj, the Euclidean distance. This is a variance. Okay, so this is just another way to calculate the variance, right? And it's subject to the first constraint and the second constraint. The second constraint is just the to preserve the local distance in the embedded space. This optimization problem is not convex. And somehow we can reformulate it as a convex problem, right? Using this relationship. So if we introduce a new variable and rewrite the original problem, we get something like this. Okay, the optimizing problem now is converted into a convex optimizing problem. The object function is the trace of the actually this is a kernel matrix, and the first set of constraints says the kernel matrix must be positive semi-definite, right? And this corresponds to the mean is of the embedded space is at the origin. It's 0, and this is preserving the distance. We can solve this problem using so-called semi-definite programming. Again, you can actually just use CVX to solve this problem. Right? For the first assignment, some of you actually applied CVX to solve SVM. Here, you can use CVX to solve this SDP problem as well. And after you found the K, the kernel matrix, you can use MDS to calculate the coordinates, the projected, the embedded coordinates. Okay, so here just show you some of the results. It's interesting, right? So given such a data set, and eventually you can unfold the data set into 2D in this case, okay? And if you have such a data set, you can, well, basically project it into 2D. And another one. So we have some images of the same teapot, right, with different view angles, and you can project it into 2D. So that's applying the SDE to the facial images. All right, some advantage and disadvantage. The main disadvantage of SDE is the semi-definite programming. It's computationally very expensive. It cannot scale to large data set. Okay, although it's polynomial time, because the problem is convex. So we do have a polynomial time solver for SDP, but the computation is very expensive. So it's limited to like around 2,000 data points. All right, so but in terms of performance, actually SDE works best than the other a few nonlinear embedding methods. Okay, and it turns out that all of these methods have a connection with kernel PCA or kernelized PCA. Next week, we're going to talk about given a linear method, how can we extend or kernelize that linear method into a nonlinear version? So we will spend some time on kernel PCA and kernel LDA. But there's a close connection between all of these nonlinear manifold learning methods with kernel PCA. It turns out that for all of these methods, if you just define a different kernel matrix, then all of them can be formulated as kernel PCA. I upload that paper to the course forum as well. You should read that paper. All right, so that's all for today. Any questions before we go? All right, that's all.